previous videos, we discussed the binomial distribution. So the binomial distribution is arguably the most important distribution that's related to a discrete random variable. So the notation we used was that x stood for the number of successes in k trial or in n trials. And so we were interested in these multi-stage experiments with only two outcomes. And we developed this notation, capital X, and this distributed like BNP. So it was implying that the binomial distribution depended on how many trials and the probability of success. We also developed a formula for the mass function. Now, this is okay to use if n is kind of small, right? So let's say 10, 20, something like that. But it's pretty inconvenient to use for large n, right? So for instance, if I said, all right, my variable is distributed binomial where n is 10,000 and p is 0.3, I would, if I want to find the probability that x is going to be greater than 201, this is annoying. It's annoying to do by hand and from the formula. So if you need a number, you should use technology. So you should use something like software R. But if you want to do theoretical work, then this is not very good. It's challenging, it's cumbersome to use. And what we're going to do, and this is a very sort of high-level theme in math and applied math, is that if you've got something complicated that you have to work with, make an approximation instead. Try to come up with a very smart and accurate approximation that is easier to work with. So we are going to consider a special case. Okay, we're going to talk about what are called unlikely events. And in this situation, we are going to talk about events that are rare but do occur in many, many trials. And I shouldn't say in, but over many trials. So to quantify that, we're going to say that p is close to 0 and n is very large. And we're going to make a special assumption. So we're going to talk about what happens when the number of trials gets larger and larger and larger, and we are going to assume that n times p, we're going to call it lambda, and we're going to say that it's fixed. It's like a constant, it won't change. And we're going to need to do that in order to make some of the math details work out. And remember, from binomial, this was the expected value, np. So we're going to be assuming that the expected value is fixed. So we're going to be talking about binomial trials where it's very unlikely to get success, but they do happen every once in a while. And what we're going to try to do is make an approximation of the mass function, and hopefully it's easier to use. So that's our idea. Now, the mass function that we are going to be interested in is the binomial mass function, and we're going to be taking the limit, right? Many, many, many trials. So we are going to be interested in that case. And mathematically, this is going to work out to something that kind of looks ugly to begin with. Because remember, these formulas for the mass function, they all involve factorials. Now, since lambda is n times p, we are going to make a little replacement. We are going to say every time we see the letter p, we are going to replace it with a lambda over n. So we'll have a limit, n going to infinity, x factorial, n minus x factorial. And now we'll get a lambda over n to the power of x, 1 minus lambda over n to the power of n minus x. So the next thing that we're going to do is we're going to try to make this look much, much nicer. And to do that, we're going to try to compare this to something. So n factorial over n minus x. You should remember that factorials have this nice property where you can write a bigger one in terms of a smaller one. So for instance, if I had this, I could write it as 2 factorial 3 times 4 times 5 over 2 factorial. This goes away. I get 3 times 4 times 5. Now, what's important is not the number here, but the number of terms that I'm left with is going to be 5 minus 2 is 3 terms. So that's related to the number that was upstairs and related to the number that was downstairs. Now you're saying, well, why do I care? Because what I'm going to do next is going to look a little bit complicated. Rather than having those 2 factorials the way they are, I'm going to write it as some ugly number. It's going to be n minus x plus 1. So the next number after the factorial in the denominator. And then it's going to go all the way up to n minus 1 times n. And that's essentially a simplification in the same way that I wrote that stuff in blue. I'll still have the lambda over n to the power of x, 1 minus lambda over n to the power of x. Okay. Now, I like this. I like this because it's going to cancel things out, and I'm eventually trying to get rid of factorials as best I can. The next thing I'm going to do is move this downstairs, and I'm going to swap this out. This is just a little bit of a reorganization. So I'll have n minus x plus 1 all the way down to n minus 1 times n. All of this junk over n to the power of x, lambda to the x over x factorial, 1 minus lambda over n to the power of x. Now, the other thing that I wanted to make note of is that whatever this weird product is upstairs, 3 times 4 times 5, I can figure out the number of terms just by taking a look at the number of factorial on the top and the bottom. So down here, the number of terms was n take away n minus x, which is x terms. Whatever x is, that's the number of terms I have upstairs. And that's going to be important for me in just a moment when I want to try to clean this up. Now, I've forgotten over here that this is n minus x, and that's n minus x as well. So the idea here is that now I can clean up that part. Okay. There are x terms in each of the top and the bottom here. And to clean up this expression, I'm going to factor out a power of n from everybody upstairs. So I'm going to factor out an n from each one of those terms upstairs. So I'll have, because I have x of them, I'll have n times n times n times n all the way up. And so that'll be an n to the power of x. And then I'll have 1 minus x plus 1 over n, and all of this junk all the way down to a 1. And that'll give me an n to the power of x there. Now, don't get too wrapped up in the details. What's important here is that, yes, we have the correct number of terms upstairs and downstairs to be able to cancel out in just a moment. So these terms will cancel out, and that's what's important here. So it does start to get a little bit heavy, and that's totally understandable. What's important here is that there are a whole bunch of terms being multiplied. And in a moment, we are going to talk about their limit. And we are just massaging everything so that it looks nice. Now, another thing that I'm going to do here, sorry, I keep making little errors. This is an N. This is an N. I'm going to take this part and I'm going to write it as a product. And so again, all of this stuff is just me working on algebra details. Algebra, algebra, algebra. So it's nothing very exciting here. But it's all the details that go into this. And I'm finally ready now to ask, okay, I have a limit of this big mess. Could I take this limit? Is it even possible for me to do that? Okay. And so the idea here is that anything with an n is variable and anything else is a constant. So for instance, this term right here would be a constant. So this thing is a constant, so its limit exists. Many of these other terms, for instance, this term, so when n goes to infinity, that's a constant. When n goes to infinity, 1 over lambda to the n to the power of negative x, this term wants to go to 0 because lambda is a constant, so this term wants to go to 1. That exists. Everything in this weird product, so all of the terms here, every single one of them, at the very worst, all of those things individually want to go to 1 because so many of these denominators have an n in the bottom, so this entire product together will go to 1. Now, the trickiest part of all of this is the last term here that you may or may not remember. Some point, some math teacher in calculus class may have tried to tell you that this is the definition or a definition of an exponential with a natural base. And so again, don't feel too bad if you can't remember that, but this turns out to go to have a limit of e to the minus lambda. So in fact, all these limits exist. And that means if I were to apply the limit laws, I would end up getting x to the lambda, lambda to the x, x factorial, e to the minus lambda. And it's a lot of algebra and a lot of work. So in the case that this lambda equals np is fixed, and we get n to infinity, we end up getting what's a new or an approximation to this mass function. So in this case, we would say that the mass function when big X is equal to little x is e to the minus lambda, lambda to the x over x factorial. What is this thing? This is what we are going to call a Poisson distribution. And so in this case, we will say that our variable is distributed like a Poisson distribution. And in this case, lambda, this parameter, is the only important part. X, again, will be the number of successes or occurrences of our event. Remember, we are trying to model a rare event. We are trying to figure out how often this would happen. There's a lot of math in this first video. Now, don't worry if you can't follow along or you say, I'll never be able to memorize it. I'm not going to need you to memorize or be able to go through that proof, but this proof isn't given to you anywhere. And so I do want to show you that it comes from a natural assumption and you can come up with it using tools you already know. Now, if this really is a mass function, this should equal 1. And so what you would do is you'd then take a sum and say, okay, well, x is the number of occurrences of a rare event. Does this thing sum up to 1? And what this turns out to be is actually an infinite sum. E to the minus lambda, x equals 0 to infinity, lambda to the x over x factorial. You get a gold star if you remember from Calc 2 that this turns out to be the Maclaurin series for e to the lambda. If you don't remember, that's okay as well. And so you'll get e to the minus lambda, e to the lambda. This does equal 1. Okay. Now, there are equally boring mathematical ways to come up with expectation and to come up with variance. They all come from the definitions, but you could use the definitions to get the following, that the expected value is just going to be lambda, and that's expected, no joke, because Poisson is just supposed to model binomial, and for the binomial, the expectation is NP, and it will turn out that the variance is also NP. Now, this one is kind of funny, but remember, for a binomial, the variance is NP 1 minus P. And if you think about this, NP is a constant, and P is approximately 0. So then this goes to lambda, or n times P times 1, as n goes to infinity, right? 1 minus something that goes to 0. So this video has just been about deriving this weird distribution. We are next video going to use it and show you why somebody may want to use it, how they may use it, and we'll take a look from there.